Hello and welcome to the next of the lectures under this course titled Approximate Reasoning Using Fuzzy Set Theory. In the last lecture, we have seen that operations on fuzzy sets can be seen as the operations on the corresponding unit interval 0,1, which is its codomain. We have also seen that there are different possible interpretations available to us for these operations, and we wondered how to choose among them. In this lecture, towards enabling us to answer this question, we will look at a very preliminary and primary structure, that of an order structure on the set of fuzzy sets. To begin with, we will look at order relations on a set and move on to looking at some order relations on the set of fuzzy sets. You might remember that we have seen that there are two types of orderings that are possible among fuzzy sets. However, we would like to also confirm whether these relations that we call as orderings on fuzzy sets, whether they conform to classical order theoretic concepts. Let's begin with binary relations on sets. We all know a binary relation on a set X can be thought of as a function from X cross X to just the set 0, 1. For instance, if we consider X to be the natural numbers, we can define for any given AB element of N, we can define a relation as follows. A is related to B if and only if A divides B. That is, there should exist a K element of N such that B can be written as K times C. Now you will see that if we define such a relation, binary relation, by the symbol tilde, we can ask the question, is 2 related to 3? Well, clearly 2 does not divide 3, so this is not 2. What about 2 and 4? Are they related? It essentially means asking the question, does 2 divide 4? We know that yes, 4 is 2 times 2. So if we see here, these are binary relations on the set of natural numbers. Now, we can have many types of binary relations. Some of the properties that are often used and employed are these. What do we understand by reflexivity? We see a binary relation is reflexive if A is related to itself for every A in the set. You will see immediately that the relation that we have defined above, that of divisibility, is actually reflexive because 2 is related to itself. The next of the properties is that of symmetry. Since it's a binary relation, we can talk about symmetry. What does symmetry mean? It means if A is related to B, then we want that B is also related to A. Now we can ask the question, is this true of the relation that we have defined above? Well, we know that 2 is related to 4. However, is 4 related to 2? Clearly, no. So the above relation is not symmetric. But of course, there are many symmetric relations. For instance, let us consider once again X to be N, and let's define that A is related to B if and only if mod A minus B is divisible by 2. Because 2 divides mod A minus B. Clearly, you will get a partition of N, equivalence classes are those of even and odd numbers. It is clear that if I number this as relation 2, 1 is related to 3 and so is 3 related to 1. So this is a symmetric relation. There are also asymmetric relations, and our first relation of divisibility falls under that. Since 4 is not related to 2, but 2 is related to 4. So asymmetry essentially means A related to B does not imply B is related to A. What is antisymmetry? Antisymmetry says that if A is related to B and B is related to A, this implies A is actually equal to B. We all know that the usual order on n has this property. That means if you have A less than or equal to B and B is less than or equal to A, then we know that A actually is equal to B. Finally, the property of transitivity. Transitivity says that if A is related to B and B is related to C, then this should imply that A is related to C. Clearly, this relation is transitive. So is this relation. What does transitivity say? It says that if A is related to B and B is related to C, this should imply A is related to C. Clearly, the natural ordering on natural numbers does have this property. So does the second relation, where 2 divides mod A minus B, a binary relation that we have defined on the natural number set. There are different types of binary relations that we can think of. For instance, if a binary relation is reflexive, symmetric and transitive, we call it an equivalence relation. For instance, consider the relation that we have defined here, that on the set of natural numbers, A is related to B under this relation if and only if 2 divides mod of A minus B. It can be shown clearly that it is reflexive plus symmetric plus transitive. So this is actually an equivalence relation. We can also have relations which are reflexive but not symmetric but antisymmetric and transitive. Such relations we call order relations. For instance, consider the relation of the usual ordering on the set of natural numbers. We know that it is reflexive, antisymmetric and also transitive. Thus, it forms what we call an order relation. Let's look at what are partially ordered sets. Let us consider a set P which is non-empty with a binary relation defined on it. We call this couple, the set with the relation, we call this a poset if this relation is an order relation. It is typical to indicate order relations by this less than equal to symbol or some variant of it, and that is what we will also follow. So a set with this relation, binary relation, is called a poset if this relation is an order relation on P. Now, it is also typical that if the set P that we are considering is actually finite, then to show the order, it is convenient to use what are called Hasse diagrams. What are they? Allow me to explain this to you. Consider the set P which has 6 elements. One possible ordering of P gives us this Hasse diagram. How do we decipher this Hasse diagram? If you take 2 elements, if there is a line between them, then these two are related as either predecessor and successor relationship. So look at 1 and Q. So 1 is related to Q immediately and Q is related to P is related to 0. But now we are talking about orders. That means there is an ordering between them, and it is common to use the language that 0 is less than P or P is less than Q. So as you go from the bottom to top, you can think of it as an increasing relationship. It is clear from this diagram that P and B are not related, nor is P and A. Similarly, Q is not related to either A or B under the ordering that we have given on this set. But we could also have another ordering which gives us this kind of a Hasse diagram. Note that by the transitivity, once you indicate these relationships, we could also extrapolate and determine the relations between any other two elements. For instance, in both of these posets, we know that 0 is related to Q, 0 is also related to B. And in fact, 1 is related to every element of the set and 0 is also related to every element of the set. Clearly, in both these posets, Q is not related to B. We could also have a poset on the same P where the relationships are such that the Hasse diagram that you get is as you see on the third diagram on the screen. An immediate question would be, why so many orders on the same set P? Well, the answer to that would be, it can infuse very interesting properties. What do we mean by that? Let's take a couple of examples. A poset is called a chain or totally ordered if you pick any two elements A and B, then they are related. That means either A is less than or equal to B or B is less than or equal to A. What are the common examples of chains that we know? If you take R with the usual ordering, we know that given any AB element of R, we know that either A is less than or equal to B or B is less than or equal to A. And similar kind of ordering exists also on N. Now, let's consider X to be R square. We can give the usual ordering, the component-wise ordering of R square. How is this defined? If you take a pair of tuples from R2, you can define the ordering like this, that AB is less than or equal to CD if and only if A less than or equal to C and B less than or equal to D. It can be clearly seen that this relation is reflexive, antisymmetric and also transitive. However, it's not a totally ordered relation. Not totally ordered relation. Why do we say this? Consider these two pairs of elements from R. Now, neither can we say this, while 2 is less than 3, 3 is not less than 2, nor can we say this, while 3 is greater than 2, 2 is not greater than 3. So you have at least a pair of elements which are not orderable under this relation. Can we come up with another relation which will help us in this? Consider this relation. Let X be R square and we define another relation like this. AB is related to CD if and only if either A is less than C or if A is equal to C, then B should be less than B. Now, using this relation, it can be easily verified that this is not only a partial order, that means it's reflexive, symmetric and transitive, but it is also a total order. That means any two elements can be related under this order. For instance, if you look at this 2, 3 and 3, 2, going by this definition, the moment we see 2 is less than 3, we say that this is smaller than this. Thus, we get a total order. This ordering on R2 is often known as the dictionary order or the lexicon order. So, having a different order would mean having more properties or some special types of posets. We also will look at another important property of a poset. A poset is said to be bounded above if there exists an element which we indicate by 1 such that every element is smaller than that. Every element is ordered below that. We say that it is bounded below if there exists an element below which no other element exists. Essentially, bounded above means there exists an element such that there is no element from the set which can dominate it, is bigger than that. Bounded below means there is an element in the set P such that no element of P is smaller than that. If it is both bounded above and below, we call such a poset a bounded poset. Now, consider the set N with the usual order. While this is a chain or totally ordered poset, we know that this is not bounded above. Yes, 0 is smaller than any x. It is bounded below, but there does not exist any y such that y is greater than or equal to x for every x in N. Clearly, this is not bounded. Now, let's see whether we can introduce a new order on this set. So consider a set of natural numbers including 0. Now this is the order that we are going to define on it. That x is less than or equal to y if and only if y divides x. Remember, this is a dual of what we considered right at the beginning. What do you mean by this? We mean that x can be written as a product of y and some other number L from this set n union 0. Now let's understand this relation. So allow me to write this once again. We say x is less than or equal to y if and only if x can be written as Ly, where L comes from n union 0. Now, if you ask the question then, is 2 related to 3 under this ordering? Well, clearly 2 and 3 are prime numbers, they are not factorizable. So we see that under this new ordering, neither 2 and 3 are not related to each other. And that would happen with any other prime number also. So the prime numbers are not suddenly relatable. What was once a chain has now suddenly started giving away. Given 2 elements, we are not able to order them. But then why did we enforce this order? Do we stand to gain something out of this? Well, interestingly, if you look at it, consider Consider 1. If you see, 1 is actually greater than every y for all y element of n. Why is this so? You can write y as y times 1, which according to this definition means y is less than or equal to 1. That means 1 has become the upper bound for this set. What about 0? You will see that 0 is still less than or equal to y for every y, since 0 can be written as 0 times y for any y in n union 0. So if you actually work this out, this is the kind of Hasse diagram you would get for the ordering, new ordering that we have proposed on the set n including 0. Now you will see that while we have lost the total ordered property of n that we used to get with natural ordering on n, what we have instead got is a bounded above poset on n. Now if you consider the set Z, the set of all integers, while it is a chain, it is neither bounded below nor bounded above. However, you can easily verify that if you define the order like this, then what we would get is a poset of this type, where we have introduced a new bound below, which is 0. Of course, it's still not bounded above, because there is no one unique element of Z which is not dominated by anybody else. So what we call as maximal elements are there, but it's still not bounded above. Right. Let's come to discussing some order theoretic structures on fuzzy sets. We have seen that on the set of fuzzy sets, we can give a point-wise ordering on them. So we say that A1 is related to A2 if and only if the point-wise membership values are less. That means A1 of x is less than or equal to A2 of x. This is the usual point-wise ordering of function, and we have already seen that when A1 and A2 are classic characteristic functions, then these actually coincide with the notion of subsethood on classical sets. These figures must be familiar to you by now. Now, the question now is this an ordering on the set of fuzzy sets? Well, consider f of x to be the set of fuzzy sets on x. By 1 tilde, we denote the function that takes the value 1, the constant value 1 throughout x. By 0 tilde, we denote the function which takes the value 0 on the entire x. What we can immediately prove is this nice result which says that set of all fuzzy sets on x with the pointwise ordering is a bounded poset. So that means this pointwise ordering is actually a partial order relation on the set of fuzzy sets, and the 0 tilde and 1 tilde, they act as the lower and upper bounds. Now, if you would like to see why this is an order, remember we said that A1 subset of A2, if and only if A1 of x is less than or equal to A2 of x for all x in x. Clearly, we see that it is reflexive because A1 is related to itself. If A1 is contained in another A2 ordered with respect to A2 this way, and A2 is also related to A1, clearly this means A1 of x is less than or equal to A2 of x, and A2 of x is less than or equal to A1 of x, and we know these are numbers from the 0-1 interval, which means using the natural order on the 0-1 interval, we know that A1 of x should be equal to A2 of x, and this happens for every x in x. Clearly, we are borrowing the poset property that is available on 0-1 with respect to the natural order. So, it means it is also transitive. Clearly, this becomes an order on the set of all fuzzy sets, and we get a bounded poset. You might remember that we also were looking at some other pairs of fuzzy sets which are not orderable under this particular relation that we have defined. For instance, if you look at these two fuzzy sets, with respect to this ordering, they are not orderable, nor are these two fuzzy sets. However, we felt there is something regular about the pair of fuzzy sets that you see on the right side of your screen, and hence we introduced a new order based on the level sets, the alpha pairs. So we say that if x is the real line, we define this order on all those fuzzy sets which are defined on the real line as follows. A1 is less than or equal to A2 if for every alpha in 0-1, these two inequalities are held. So according to this, we have seen that this pair of fuzzy sets is orderable, whereas still this pair of fuzzy sets it's not orderable. Now the question is this relation, even though we are calling them as order relation, we use the term that A1 is less than or equal to A2, is this actually partial order? Now, interestingly, it is immediate to see that this relation is in fact reflexive because A1 less than or equal to A1. Once again, I should make a special mention that here we could look at inf as in some sense the left endpoint of the alpha cut and sup as the right endpoint of the alpha cut. A justification for this will be provided soon enough in one of the upcoming lectures. Okay. So this relation is actually reflexive. What about antisymmetry and transitivity? To discuss that, let's look at these two fuzzy sets. Call them A1 and A2. The red one is A1 and the blue, the fuzzy set in blue is the A2 fuzzy set. Now, so as to be able to graphically see the point that we are trying to illustrate, let's try to superimpose these two sets. But please notice that these are two distinct fuzzy sets. Let's superimpose them and take a particular alpha, any alpha. If you consider the alpha cut of this alpha for the fuzzy sets A1 and A2, this is what you would get. So the fuzzy set A1, the alpha cut for that is indicated by the red line. So essentially you have to take the inverse and look at the points on the x-axis whose membership values are above that alpha. So you will see that the alpha cut in this particular case is a union of intervals, and also the same with the alpha cut of the fuzzy set A2 that's there on the bottom. While the alpha cuts themselves are different, what you would see is the infimum of the alpha cuts and the supremum of these alpha cuts are essentially the same. As was mentioned, we will interpret the infimum and the supremum of these alpha cuts at the left and right endpoints of the whole interval among the union of intervals. Now, it is immediately clear that the left endpoint of the alpha cut, the set, it's a union of intervals, so we call it a set. The left endpoint of this union of intervals of both the alpha cuts are identical, so are the right endpoints. Which means we could say with respect to this relation, A1 is less than or equal to A2, so is the case with A2 less than or equal to A1. However, we see that it is not antisymmetric, simply because A1 is not equal to A2. What this means is, even though we called it an ordering relation, we see that this is not an ordering as we understand as a partial order on the set of fuzzy sets on R. However, not all is lost. So if you instead consider the set of all convex fuzzy sets on R, let's denote it by CF of R, then it can be easily shown that on this set of fuzzy sets, convex fuzzy sets on R, this ordering is in fact a partial order, and with the same upper and lower bounds as we have considered earlier, it becomes a bounded poset. The proof actually is based on the ordering of intervals. Clearly, a quick proof would look like this. If you consider two convex fuzzy sets, let's for a moment think of it like this, and take any alpha cut, we know that the alpha cuts of convex sets are intervals. Alpha cuts of convex fuzzy sets defined on R, they are intervals, and essentially the definition here is about the ordering of intervals. So based on that, it is easy to see that this will become a partially ordered set with respect to this order. Well, a quick recap of today's lecture, we looked at binary relations, especially partial order relations. We have seen that at times there is need for different orders, as we have seen also in the case of fuzzy sets. There are two different orders, and because they often lead to some special posets, and based on what we have seen on ordered sets, we have been able to look at the ordering that we have introduced earlier in one of the earlier lectures as actually being partial orders, either on the entire general power set of fuzzy sets or on a specific class of fuzzy sets, namely that of convex fuzzy sets defined on R. Now the question is, what lies ahead? In the next lecture, we will look at yet another special poset which we call the lattice. We will look at the lattice of fuzzy sets, and hopefully this will allow us to discuss one of the questions that we have raised in a previous lecture, where we discussed that there are many possibilities to interpret operations on fuzzy sets. How do we choose among them? This line of exploration will clearly show us what each operation brings to the table. So next lecture, we will look at the lattice of fuzzy sets. Thank you once again for joining me. Hope to see you soon in the next lecture. Thank you.